probably. And then we're going to talk about iterative methods, well, and linear systems in general. And finally, eigenvalue problem. So these last two parts will be more numerical, and these first two parts will be more theoretical. All right. So linear algebra. So there's two ways of doing linear algebra. The first one is the linear algebra that you code on a computer, which is concrete linear algebra in a basis. And the second is abstract linear algebra that you learn in classes, so with vector spaces and linear operators and so on. Okay, so there's abstract versus concrete linear algebra. So concrete linear algebra is Rm. Abstract is let E be a vector space. Okay. What does it change? Not too much. It's just a question of formulation, right? So okay, we are going to talk about finite dimensional linear algebras in this series. I will prefer this kind of things usually because it makes things easier to formulate. But in the end, when you want to go on a computer and you want to code stuff up, you go to concrete linear algebra, meaning you fix a basis and then you do your computations on a basis. Okay. So that's the first distinction. So first, what is linear algebra? Linear algebra is the study of linear phenomena. So everything that is linear in nature, be that dynamical systems, systems of equation, and so on, this will be the topic of linear algebra. So abstract versus concrete, there's a second distinction that one can make for linear algebra, which is algebra versus analysis. So algebra versus analysis, for the mathematicians, algebra is everything that has to do with equals. Analysis is everything that has to do with inequalities. So this is structure, this is limits, things like this. Right? So linear algebra is kind of between both. So it's algebra in nature, of course. You manipulate things, you make algebraic transformations and things like that. But it's also the methods that are used in linear algebra. Some of them are analytic in nature. So depending on the topic, often you can prove the same thing with algebraic versus analysis techniques. So for instance, if you want to prove the spectral theorem that every matrix, symmetric matrix, can be diagonalized in the orthogonal basis with real eigenvalues, the first step for proving this is to prove that every matrix has an eigenvalue. The algebra method for doing this would be to say that the characteristic polynomial is a polynomial and therefore has a root in the complex domain. This is a purely algebraic. Well, no, I mean to prove this theorem actually you need analysis, but it's an algebraic statement. The analysis proof would be to say that you can minimize the Rayleigh quotients and prove that this has a minimizer, and the minimum of the Rayleigh quotient is an eigenvalue. And that will give you the existence of an eigenvalue. Okay, so often there are methods that are algebraic with polynomials, normal forms, things like this, or analytic. Also, for instance, if you want to solve a linear system of equations, you can do Gaussian elimination, which is pure algebra, just replace in systems of equations, or you can do iterative methods that will hopefully converge to a solution, which is pure analysis. So mostly in this series of lectures, we're going to be concerned about these two things, mostly because it's the most natural method when you go to quantum mechanics. Quantum mechanics often involves infinite dimensional functional spaces, and this is a lot easier to talk about in the abstract. Let H be a Hilbert space, and with analytic methods, because these methods are very specific to finite dimension usually. Okay, good. Right, so vector spaces, linear applications, linear maps, norms, and so on. I'm assuming you know already what those are. I will just briefly recap the notations, and in particular, the different sets of notations that will be used in different communities. So you will have, let's say, abstract linear algebra or functional analysis. Functional analysis is linear algebra in infinite dimensions. Concrete linear algebra and quantum mechanics with Dirac notations. So I'm just going to give some notations that people use in domain. So for vector spaces, this will usually be called E. This is Rn in concrete linear algebra. And this is an abstract Hilbert space for quantum mechanics. Okay. I mean, this is all equivalent. This is just setting the notation so that you don't get confused if you're used to thinking in terms of quantum mechanics or in terms of basis. So a vector in this abstract space you will denote by maybe U if it's a function, you will denote by X if it's a vector in concrete, or you will denote in Dirac notation by the ket psi. Yeah. What else? If you have a linear operator, maybe you call it L here. You call it definitely A in concrete linear algebra when you have a matrix. So A, so Xi, we call, yeah, X is the collection of the Xi. A is the matrix with coefficient Aij. And here it will be an operator. And people put these funny little hats to remind themselves that it's an operator. Okay, what else? Inner products. So in abstract linear algebra, you write it like this. Write it like this in concrete linear algebra. And you would write it as this in quantum mechanics. Okay, why not? Just a question of notations. What else? Adjoints. Okay. Adjoints, if you have an operator L, you define the operator L star, and you define it how? You define it by U L star V is equal to LU V. This is the definition. In concrete linear algebra, you would just define A star Ij by Aj I bar. Complex conjugates. Okay, and in quantum mechanics, of course, we define it as psi H star phi is equal to. Sorry, and you put bars here, and here you put commas. I know.
Normally we use the dagger in physics.
Ah, yes, but I don't know how to draw daggers. So you could, yeah, okay. Yeah, no, that's right. Right. I will use stars mostly, probably. Okay, and so on and so forth. I mean, so for instance, if you have the composition of two linear operators, you will define them here by how they act on vectors. You act with one and then you act with the other. If you are with concrete linear algebra, maybe you define it as a product of matrices. Okay, AB Ij is equal to sum of A, I, K. Wow, this is hard in English. B, K, J. Okay. Everything clear with this? And so, for instance, the ket here will be sorry, we'll call this. Here will be a star. So this ket here in concrete linear algebra you interpret as a row vector. Okay, this is MATLAB. If you've done MATLAB, this is maybe what MATLAB uses, or even other systems. So this you see as a line vector, as a line matrix. Okay, it's a matrix with one row and n lines. Sorry, one row and n columns. And here you would see as the map that to V associates UV. Yep. Everything good on this? Okay, so this is direct notation. And then let's start to actually do some math. Okay, so again, yeah. Yeah. Usually in linear algebra, the convention is that if you have a vector, it's a vector matrix. It's a column matrix. This is, I believe, pretty universal. It's the Fortran ordering if you want, but it's. Yes.
And then when you write to C, everything is
no, but this is also consistent because if you have a row matrix or a vector matrix or a column matrix, you have no issue with ordering. I have no idea with Mathematica. No. Ah, yeah, okay. Okay. Uh-huh. Yeah, but in memory, it's the same. I don't know. The reasonable thing to do is to define that a vector by default is a matrix with the columns. This is consistent with matrix vector product and so on. Yeah. Okay, so okay, now let A be a matrix. Oh. So I will not necessarily be super consistent. I will switch back and forth between all these notations according to what is the most convenient notation for the purpose. We can define a bunch of subspaces. So first we can define its adjoints, right? Star, you define it in this way. Everything is okay with the fact that this definition is the same as this definition with the standard inner product. No need for me to do the proof. Okay. The important bit is that here, so here and here, you just assume a vector space and an inner product. You don't specify what those are. Here, you select a particular inner product, which is the Euclidean inner product, the sum of xi, yi. Okay. This has a number of things that are maybe not intuitive a priori. This definition of the adjoint depends on the inner product. Okay? Depends on the inner product, on the dot product, on the vector product. If you change the inner product, and you can, I mean, there's no unique inner product. You can definitely change the inner product. You can put weights on specific components and so on. If you change the inner product here, you will change this adjoint. Okay, just because it's involved in the definition. Here it's not clear, right? Because this is the definition of the adjoint in the concrete thing. But of course, this hides the fact that here you select a specific inner product and you don't change it. Okay, so you always have to remember that whenever you write a dagger or a star or a transpose or a T or something, it means that you select the particular Euclidean inner product. Okay, and it's not, I mean, you can definitely play with the inner products. So for instance, the gradient methods, the gradient is only defined up to an inner product. If you change the inner product, you change the gradient methods. Yeah, so there's a number of things to unwrap. Anyway, so okay, I have a map from R and to R. Yes.
It would depend like this equivalence would depend on the boundary conditions, maybe. You know, when you integrate by parts, you put the
Yeah.
so there is a boundary condition, boundary term that would cancel the conditions.
That's not quite right. So first, of course, I'm doing everything in infinite dimensions, so there's no question of boundary conditions and so on. But even when I talk about inner product and so on, I don't mean this. I mean that you can define this, and this is a perfectly valid inner product.
Can also like be able to write concretely.
Yeah. No, I mean, this is Rn, right? There's no boundary condition in Rn. Work in the finite basis.
Yeah.
I'm assuming that you mean for operators, then you need boundary conditions, and because you need the domain of an operator for self-adjointness and so on. But this is, I'm not going to touch that. Yeah. Okay, so one very useful thing to think about. Okay, of course you know about the range of an operator, the kernel of an operator. So operator, linear map, matrices, I will be using this pretty much synonymously. So there's one very useful relation that maybe I start by writing, which is that the image of A orthogonal is the kernel of A transpose. I start. Okay, so I'm assuming, yeah, this is Rn to Rn, so this is real vector spaces. So I'm not going to bother with complexes here. So, okay, this is the first non-trivial thing I'm going to write. This is a statement that is always true for any linear mapping like this. And it's an important one because it clarifies a number of things. So first, is it true? So what does it say? The image of A is the set of points you can reach by applying A. It's the set of AX for X in Rn. The orthogonal just means that I consider all the vectors that are orthogonal to the vectors in image of A. The kernel of A transpose. So, okay, maybe to clarify this, I write it like this, Rn to Rm. To clarify a bit. So A goes from this, A star, A transpose, goes from Rm to Rn. Okay. And this holds. Okay. Why does this hold? Because you write this. Okay. By definition of A transpose. So now, if you consider, so I will mess this up. If you consider a vector in kernel of A transpose, so if X is in kernel of A transpose, it means that A transpose X, Y is equal to 0 for all Y. And therefore, that's X, A, Y is equal to 0 for all Y. And therefore, that's X, Z is equal to 0 for all Z in image of A. And therefore, that X belongs to image of A. So, right? So that's one inclusion down. So I assume that I have a vector here, and I show that it belongs to this. And you can do the reverse. If you assume that you have a vector in this, I mean, okay, I'm not going to, okay, maybe I write it because there's one non-trivial step there. So if I have now Z in the orthogonal here. So yes. This is for all y's in Rn. Okay, so now if I have a z which is in image this, then I have z against. Okay, I'm going to confuse myself very quickly. No, so I have x. This is an x. So I have x ay is equal to 0 for all y, and therefore h transpose x y is equal to 0 for all y, and therefore h transpose x is equal to 0. And therefore x belongs to h transpose to the kernel of L. Yes? Yes, sorry. Yeah. Right. Okay. So that's the proof. You may wonder why I'm doing this. This is good because with this, we can write what some people call the fundamental subspaces for an operator. And it's a generally useful thing to have. So I can define sorry, the image of A, the kernel of A transpose. Yeah, we write the image of A transpose, and here we write the kernel of yeah, the kernel of A, yes, 0, 0. So you have relationships like these. Okay, this is a very weird diagram, but it's a very condensed way of writing the subspaces for a matrix. So what does this mean? This splits the space. Okay, this guy is the orthogonal complement to this guy. Similarly, this guy is the orthogonal complement to this guy. This is exactly what these relations prove. Okay, this guy orthogonal to this guy. So you can split the space orthogonally, both for x and for y, into those subspaces. Okay, and then you have this kind of shapes. So the only thing, so this is of dimension r. This is the rank of A. Okay, this is of dimension. What is this now? So this, because this is the orthogonal complement, this is in M. So this is M minus R. And here, so what is the rank of these guys? This rank is R, and this rank is N minus R. It's not completely trivial that this is true, but this is the rank nullity theorem. Yes, this you can, so the rank, the dimension of the image of A transpose is the same as the dimension of the image of A, and this is a consequence of the rank unity theorem, and this you can see most easily from the SVD, for instance. I will explain the SVD if you don't know it. But from the SVD, you can see that those two things are the same. Okay. So why might this? Okay, this was just to draw some arrows and so on. Okay, why might this guy be useful in practice? So this relation sometimes is called the Fredholm alternative. It's infinite dimensions. It's saying things that are interesting. So assume you want to solve Ax is equal to b. Okay. A square, for instance. Just to make things simpler on myself. If A is invertible, this is fine. Okay? There's a unique solution, my life is good, everything is good. What if A is not invertible? If A isn't invertible, what is the solution of this set? Or what is the solution of these equations? I mean, first, it cannot be unique, right? Because if this guy is non-invertible, there's something in the kernel, okay? And therefore, if I can add that to my solution, to any solution, and get another solution. So it's not unique, that's for sure. Does there exist a solution of this equation? It's not completely clear. It's not completely clear because B might not be in the image of A. Right? But this theorem gives you a very easy way to test if B is in the image. Right? Because we know that the image is the orthogonal complement of the kernel of A transpose. So this has a solution, and actually infinitely many solutions, if and only if B is orthogonal to the kernel of A transpose. Right? So you have a very quick way of checking whether your system will have a solution. It will not have a unique solution, this is for sure, but you can check whether it will have a solution. This is a very, very fancy way of saying something very easy, which is, as often in maths, some people would say, which is, assume you have a linear system, 2x plus y is equal to 4, and I will take twice this, 2y is equal to 7. Okay? Of course, I mean, if the coefficients here are good, the matrix is invertible, but here I took this one to be twice this one, so this matrix is not invertible. The matrix encoding this linear problem is not invertible. At what condition will this equation have a solution? The right-hand side has to be compatible. Right? This equation is twice this equation, so this 7 has better be 8 if I'm to have a solution. And if that is the case, then the set of solution is simply given by this, by the set of solution to this equation. Okay, what does this mean that this guy must be 8? It means that this right-hand side has to be orthogonal to all the combinations. So here I have L1, sorry, 2L1 plus L2 is equal to 0. If this is the first line, if this is the second line. What is this saying in linear algebra terms? It's saying that 2, 1 belong to the kernel of A transpose. Right? Because vector products are combinations of columns. So vector product with the transpose is combinations of rows. Yes? Sorry. No, so 2 minus 1. Sorry. This is 7. Oh, this is 0, yeah. This is, okay, so sorry, by L1 and L2, I just mean the lines of the homogeneous equation. So A is 2, 1, 4, 2. And this I call L1 and this I call L2. All right? So the fact that this is linearly dependent means that 2L1 minus L2 is equal to 0, which means that 2 and minus 1 is in the kernel of A transpose. And so if I have to have a solution, I have to have that B is orthogonal to 2 minus 1, which is exactly the condition. But this 7 must be 8. Yeah? Okay. So this was just to get us started with this kind of reasoning. So in general, you have a map. You have this subspaces. This guy might be a proper subset. It's not the whole space of the space. And the orthogonal complement is given by this. And you can play with this kind of diagrams. Yes. Yep.
So if it was equal to 8, the second line, you would say that this thing is
Is underdetermined. Under it's
so
yeah,
say,
underdetermined.
so A is not equal to 2, it's the same as the other under.
If it's square, yes. Yeah, because it means that some rows are redundant. Oh no, okay. So it depends. If this 7 here, this is overdetermined. And if it's 8, yes. But then it overdetermines the solution so much that there's no solution. But if this 7 is an 8, this is underdetermined because there are many solutions. Okay. So let's continue with this kind of general statement in linear algebra before moving on to more applied stuff, I would say. The spectral theorem. You all know the spectral theorem. The spectral theorem is, so A again is from Rn to Rn. Yeah, so I will be working on real functions, on real vector space just to make my life simpler, but it's the same complex in this. If you do quantum stuff, you don't need me to tell you that, you already know. So if A transpose is equal to A, then A is diagonalizable, in so normal basis with real spectrum. So each part of this statement is important. It's diagonalizable. Okay, this is maybe the least important bit of the theorem because almost every matrix is diagonalizable. Okay, so eigenvalue, eigenvectors, you don't need me to define what those are. You already know. A matrix is diagonalizable if you can find a complete set of eigenvectors. Almost every matrix is diagonalizable because almost every matrix has the isolated spectrum, non-redundant. What is it called? Simple spectrum, meaning every eigenvalue is simple. Yep. So in the sense that, okay, I'm not going to say that in detail, but see, if you have A which is not diagonalizable, then let's say it like this: the set of B matrices such that A plus epsilon B is non-diagonalizable for epsilon small. This is of dimension less than the forcing. So this is a vector space, right? No, is it a vector space? So it's of Lebesgue measured 0 at least. Okay, so for almost, if you pick a matrix at random, a matrix B at random, then A plus epsilon B will be diagonalizable. So for instance, if you pick this matrix, which is like the prototypical example of a non-diagonalizable matrix, you perturb this by a bit. For this to keep being non-diagonalizable, you need to essentially not put anything here and perturb in the same way here and here. So you need really a lot of conditions. So that if you pick a generic B matrix, it will stay. It will be diagonal. Anyway. Yeah. Every matrix is the limit of diagonalizable matrices, but it's even more than that. It's the limit in almost any direction. Almost any direction you pick will be good. But I'm not going to talk about that too much. So yeah, I was just saying that to motivate the fact that this guy is not the most important bit. Probably this guy is. The basis is also known. Okay, and the spectrum is real. So how do we prove this? You've probably done this once in your lives a very long time ago. So let's refresh that memory. Okay, first step. So this will show by induction. The first step is to show that A has an eigenvalue. First. Okay, first bit is real spectrum. This is easy, right? If AX is equal to lambda X, then what do we do to show that this guy is real? Yeah, we take the transpose, so we get that X AX is equal to lambda squared. So X is non-zero, so I can divide through. So lambda is this. This is, of course, a very important quantity, which is called the Rayleigh quotient, super important quantum mechanics. So, okay, why is this guy real? XAX? Because when you take its conjugate, you find zero. And normal evaluations. Tell me if you want to, so I'm going to skip over lots of these details. So tell me if you want me to do some of this. Okay, so then this is real. Okay, and you use, of course, use this bit to prove that. Okay, so this is that bit now. The spectrum is real. Okay, so that was the first bit. The second bit, why does there exist an eigenvalue to a matrix A, to a simple joint matrix, to a symmetric matrix? Well, so there's one answer, which is the fundamental theorem of algebra, which is to say these guys are roots of the polynomial, of the fundamental polynomial. What's it called again? It's the characteristic polynomial. Thank you. So you see, this is algebra stuff. So I'm not going to talk about this very much, and I don't even know the name. So this is one method of proof. The second method of proof is saying that lambda 1, which is defined by the min of eigenvalues of A, this is equal, this is definition. So this is equal to the min of X AX over XX for all X non-zero. Okay. This is true, but you don't need to assume or even show that this is true in order to prove that there is a single eigenvalue. The point is that if there's a minimizer of this guy, or even a critical point of this guy, then it will be an eigenvalue of A. How do you show that? Well, you just take the gradient of this guy, and you find that the gradient of the Rayleigh quotient is AX minus lambda, the Rayleigh quotient times X. Okay, so if you take the gradient of this Rayleigh quotient, and if the gradient is zero, it means that you are at an eigenvalue, at an eigenvector. But this is also the proof, right? Because here we are minimizing something, and by scaling, I can also say that I take this to be X of norm 1. I can also do that. And therefore, I'm looking over the sphere, and I'm trying to minimize something which is very continuous on the sphere. Okay, and now I can use the theorem of analysis that says that if I want to minimize something over a compact set, I will have a minimizer. Okay, you see, you plot it as a function of the phi and psi coordinate and theta coordinates, for instance. It has to have a minimizer somewhere. Okay, yeah.
Maybe very naive question. What guarantees you that the Rayleigh quotient has a lower bound?
Because it's compact. It's you just plot it as a function. It's on the sphere. Why not? If you plot any function over a compact set, any continuous function over a compact set, it will be bounded. Sorry? And there's no singularity. This is it's a quadratic function of the coefficient, so it's a continuous function. So if A is not dimension, what might happen is that this guy will have imaginary parts, and therefore I cannot minimize. But you see, I mean, you plot it as a function of the coordinates, right? It's you put the theta here, phi here. It has to have, I don't know, some structure. It's a continuous function of variables. So for sure, it has a minimizer. Yeah. Yeah. So yeah, this is the important point. Here, I've used the theorem that a continuous function on a compact set has a minimizer. Furthermore, in finite dimension, if you have a bounded and closed set, it's compact. This is not true in infinite dimension. And indeed, in infinite dimension, whenever you have a continuous spectrum, then this does not hold. I mean, this minimum is not achieved. But here, in finite dimension, it's the case and everything is good. Okay. So this exists, right? So this minimum exists. It's achieved at a particular point. This particular point is an eigenvector because the gradient is 0. And the gradient of this being 0 means that it's an eigenvector. And therefore, there exists an eigenvector. Okay? So there exists an eigenvector, always. Now, I will call this X. It's 1 minus. Now I look at A. So I complete X1 into an orthogonal basis. I can do this because I have the Gram-Schmidt process, which maybe we're going to talk about later. So I complete this into an orthogonal basis and I write A. So that's X1 to Xn, an orthogonal basis. And I write A in this basis. Okay, so I have X1 here, X2 here, and similarly, X1. Okay. What can I write here? Yeah, lambda 1 and here 0. Because I know that X is an eigenvector. So I know that AX1 is equal to lambda 1 X1. Okay, so automatically here I have a 0. Okay, here I have something. Here, what do I have? 0. Why do I have 0? It's self-adjoint, it's symmetric, and we are in an orthogonal basis. This is important that this basis be orthogonal. Otherwise, that wouldn't hold. Yeah, symmetric matrices are symmetric when you write them in orthogonal basis, not in not orthogonal basis. And therefore, I have something else. Yeah, I have some A tilde, I don't know, which is of dimension one less. And I can just iterate. Okay, and by induction, I will diagonalize my full matrix. So you see, so then, yeah. Yeah. The matrix won't be symmetric anymore, that's right. I mean, to prove that it is orthogonal, you need to be able to write something like Aij equal to AI, AJ. And therefore, then you can switch. But to be able to write this, you need that the set is an orthogonal basis. Otherwise, you cannot use this formula. This formula is only true if the E's are orthogonal. Right? If you have a non-orthogonal basis, you write down this formula, it doesn't work. So maybe I don't know. Okay, can I do this like this? This is a symmetric matrix on this basis, and it sends E1 to E2 and vice versa. And now if I do, I don't know, V1 is equal to E1 and V2 is equal to E1 plus E2, I can probably try to figure out what is the action of, so A V1 is equal to V1, and A V2 is equal to, no, so here it doesn't work, of course. I have to put something like this, E1 plus 2. Yeah, because of course this was an orthogonal, was it? So this one is A1, c'est pas V1? Ah, yeah. AV1 is equal to E1 is equal to E2, and E2 is, so it's V2 minus V1. And AV2 is equal to V2. And therefore, the matrix in this basis is AV1 is equal to V2 minus V1, AV2 is equal to V2. And yeah, so matrix is symmetric, is only symmetric when you write it. So this is linked to what I said before, right? The notion of symmetric is linked with the inner product. If you change the inner product, or if your basis is not symmetric, is not orthogonal, then things break. So transpose, transpose and orthogonal are reversed because they are linked. No, it's not because of that. It's a nice way of saying about it. This is linked with this. Anyway. Okay, so this was the proof of the spectral theorem. Any questions, comments? I've written down this in telegraphic style, but this is an actual proof. Right? Put the petit carré and so on. It's a real proof. Okay, so what else? Yeah, so we've seen the variational principle here. So what happens if you have a non-symmetric matrix? Then you're screwed. And the concept of eigenvalue of a non-symmetric matrix is very tricky. Why? So eigenvalues are good for any number of things, of course. We use them in quantum mechanics a lot. And they are good in particular for controlling the growth of repeated diagonal applications. So if you have xn plus 1 is equal to AXN, the simplest dynamical system, well, general dynamical system in n dimensions. If you have this dynamical system, so then of course xn is equal to a to the n of 0. And I'm going to speak about this because it's simpler, but of course you can do the same with a continuous dynamical system. So either that or Schrodinger equation with the matrix A is the same. So the same, but similar. So what is the behavior of this according to the eigenvalues? Well, there's a nice formula. It's called Gelfand's formula sometimes, which tells you that rho of A, so rho of A by definition is the maximum of the lambda I, the lambda for lambda in the spectrum of A. Spectrum is the set of eigenvalues. Okay? Set of eigenvalues. This turns out is equal to the limit as n goes to infinity of an to the 1 over n. This is called Gelfand's formula sometimes. So it's one nice thing about the eigenvalues is that you can compute this very easily. So why is this true? I'm not going to answer this now because I don't have the tools developed. I'm going to give a nice proof of this formula later when we'll talk about Green's functions, because it turns out that this is a very nice way of writing it. Otherwise, the standard proof of this is with Jordan normal form, but I don't like Jordan normal form because it's too algebraic. Remember, I said we were going to do analysis. So we are going to do analysis, and we are going to prove this without the Jordan normal form. The Jordan normal form, if you've heard of it, is super brittle. I mean, it doesn't work numerically. If you perturb a matrix a bit, the Jordan form breaks down. But it's fine. I mean, it's a proof, right? If you know about the Jordan normal form, it will allow you to prove it. So super nice. Anyway, I will give a nice proof later. So what is this saying? This is saying that asymptotically, so I did not define the matrix norm, but I don't really need to because it works for any matrix norm. So anything that you think of is reasonable will work. Okay, probably Nisson will talk about matrix norms a bit. No, you will prove the approximation theorem, so you will have to define it.
Yeah, that's the one that I need.
Okay, so here I don't need any, so I will not define it any. Just whatever, right? The norm of a matrix is whatever you think is the norm of a matrix will work. So what this is saying is that a to the n behaves asymptotically like this. Okay, this is true for any matrix, symmetric, non-symmetric. For symmetrics, it's of course super easy to write because for symmetric matrix you have a. So if a is equal to a, then you will have a to the a is equal to p d p transpose. We'll know about this. So an p dn p transpose. So D being the matrix, the diagonal matrix of eigenvalues, is number 1 and so 0. Okay. And therefore, when you take this big, when you take a to the n with n big, what's going to happen is that there will be one eigenvalue that will be dominant among all the eigenvalues, so dominant that everything else will be crushed, and so this will hold. D to the n, 1 over n. Okay, yeah.
So in practice, so I guess there is 2 eigenvalues that are very important.
Yes.
So in practice, you converge to the lowest negative one or positive?
To whatever is biggest. And if you have 2, then you converge. I mean, as a number, you converge to the absolute value. But of course, the eigenvector, I mean, the correspond. This is the power method, right? And this will, I mean, if the vector corresponding to the biggest eigenvalue is simple, if the eigenvalue is simple, then you will converge up to scaling to that eigenvector. Otherwise, you will converge to a mixture of both or 3 vectors.
Depends on the magnitude of the eigenvalues for a.
Yeah. Yeah. Sorry? The norm of a matrix. Okay. What do you mean? No. So this is not a matrix norm. Okay, so it's important to see that this is not a matrix norm. Why? Because this. Oh, sorry.
The question about the definition of the normal.
Yeah. Okay. So let me just write this. to avoid confusion. This is this. Any norm, but any norm that is actually a norm. The important bit is that this is not a norm. Okay, if you take this matrix, this has spectral radius 0, but it's non-zero, so it's not a norm. This is again the trick of non-symmetric and non-normal matrices. You can have a matrix that has 0 eigenvalues and only 0 as an eigenvalue, but which is not 0. Okay, so this is the Frobenius norm, but yeah. But A always have at least one eigenvalue because it's the in C, yes. Yeah. The spectrum is all eigenvalues in C. Yeah. Okay, so what is it saying? A very one important example. So okay, assume you have a matrix like this, for instance, 0, 9, 0, 8, 0, 0. Then you can plot, and I look at this relation, and I plot the components against n. Okay, so I will start here, and then I will decay. I'll show you. Okay, and I will decay at some rate, and maybe here I start here. I don't know, I start here, but I decay at a slower rate. I'm very bad at drawing, but understand more. Maybe I should have process. Okay, if you have two eigenvalues like this, and you look at the component of x, this has two components, and you look at how they decay in time. They decay like this, and at infinity, what will be left is the slowest decaying one. Okay, the reason why I'm talking to you about this is to show what can happen in the case where you are not symmetric. So consider, for instance, the matrix, I don't know, 0, 9, 100, 0, 8, 0. What are the eigenvalues of this matrix? Clearly, 0, 9, 0, 8. Okay, so the spectral radius is 0, 9. What happens if you plot the iterates of this as a function of n? Well, I mean, let's look at the system. The system, so there's xn and yn, two components. So we'll have xn plus 1 is equal to 0, 9, xn plus 100, yn. Yn plus 1 is equal to 0, 8, yn. So already I can plot, maybe I can use color this time. Already I can plot the components yn, and they will go like this. So indeed they will decay at infinity very fast. Yeah, I don't know, but they will decay exponentially at infinity. What happens to xn? What happens to xn is that at the beginning, it will not decay, right? Because it picks up these hundreds. Okay, so x1 is about 100, right? So it jumps massively, then it continues jumping, and then at some point, it goes down. But the point at which it goes down, it can be very long, depending on the non-normality of the matrix, depending on the magnitude of these coefficients here. So while it is indeed true that x goes to 0 at infinity, it does so non-monotonically. Okay, you can have transients. You have a period of time for which the behavior of the system is not dictated at all by the asymptotic behavior of the system. That doesn't happen for symmetric matrices. Well, for symmetric matrices, you have that AX is smaller than rho of AX if asymmetric. So this can happen. You have no transient. Okay. Yes.
So maybe it's a bit of a stretch, but if you do perturbation theory on non-symmetric matrix, so it means that you can have completely weird behavior at the start, like a given order, and after you.
I mean, perturbation theory for non-symmetric matrices. Okay, I wasn't planning on talking about this now, but so what's the example again? So this is the favorite non-symmetric matrix. If you perturb this a bit, you can. So if you do this, this has eigenvalue. What are the eigenvalues of this? Plus or minus square root epsilon. Right? Because you do the polynomial, it's carry, bref. Okay. So perturbation theory. It has infinite slope. So it's not good. And of course, I mean, this was a specifically degenerate case because at epsilon 0, 0, this matrix is not diagonalizable. But even if it was diagonalizable, if the epsilon here, if the non-normality of the matrix is bigger than the gap of the eigenvalues, essentially, then you will still get something very, very singular. It will be more regular. It will not be like square root epsilon, but it will have a very, very steep slope. Yeah. So it's a deviation compared to a symmetric matrix for this. You can see it like this. But more generally, normal matrices are matrices such that. So let me see if I wanted to say something more about this before. No, it's okay. So, okay, non-normality, normal matrix. A is normal. This is a definition. If A can be diagonalized in orthogonal basis. This is a definition. Yeah. So always in the same. No. For a given inner product, A is normal for this inner product in the same way that A is symmetric for this inner product. For a fixed linear product, it's normal if A can be diagonalized in orthogonal. This is not the usual definition of normality. The usual definition of normality is that A transpose A is equal to A transpose. But these two are equivalent. So what is a normal matrix? A normal matrix is almost like a symmetric matrix, except that it has complex spectrum. But that's life. So a normal matrix is almost as good as a symmetric matrix. So when I say non-normality, I mean a measure of how much the eigenvectors are non-orthogonal in some way. And it is really non-normality that is screwing us here. It's not non-symmetric. Okay. Yeah. So again, on this normal symmetric business. So I've been insisting on from the beginning on the fact that symmetric depends on the linear product. So similarly, self-adjoint and so on depends on the linear product. So let's see what changes when you change the linear product. So if I define a linear product like this, I will put MSDP, symmetric definite positive. This defines a linear product. Okay, you just check the axioms and you see that it satisfies the linear product. So why not? So what is the M adjoint of any matrix M A? Okay, the M adjoint is not very good notation. This is defined. No, sorry. Sorry. This is defined by the relation AM adjoint. So I should say, why is this useful? Because it's very useful in practice to change inner products and to have non-standard inner products. So one way that can come up is that if you are discretizing an equation on a basis that is not orthogonal, then you have a mass matrix. Okay, and the inner product is the inner product with this mass matrix. So usually this is called S implications.
Mass matrix is what we call
Overlap matrix. Yeah, sorry. Yeah. Yeah, this comes from mechanics. And also, I mean, maybe you've heard the term Sobolev spaces by mathematicians, only mathematicians. And Sobolev spaces, you have different inner products that gives you different properties and so on. So it's useful to do this kind of thing. So let's compute a M adjoint. Oh, sorry. This, of course, is for the M inner products. Okay. So let's compute this. MAY is equal to X A M adjoint transpose MY. And therefore, if I want those two to be equal, I can set A M adjoint. This is not a standard notation, this M adjoint. What do I have to do? I have to do this transpose is equal to M A M minus 1, and therefore A M adjoint is equal to M minus transpose A transpose M transpose. So you see it very explicitly. If you change the inner product, you change the adjoint. So one way this can be useful is that sometimes you get matrices that don't look like they are symmetric. They don't look like they have structure. They don't look like they are very nice, but they are in fact nice. So for instance, if I have a matrix A was equal to BC, and BC is the product of symmetric definite positive matrices. So there are plenty of concepts, or maybe, I don't know. One is symmetric definite positive, and the other is just symmetric. This comes up in a number of contexts. In chemistry, you can find this in TEFT equations, for instance, linear response TEFT equations. You have things that look like this. If you linearize the self-consistent equation, on Sham or Archie-Fock or something, you find that the linearized has this kind of form as well. Yeah, sorry, SDP is a symmetric definite positive. So symmetric with strictly bigger than 0 eigenvalues. Probably, yes, this is French. This is probably French. Yeah. SPD. Yes, sorry. SPD, yes. Yes. It says DP en français, c'est symétrique définitive. Sorry. SPD. Yeah. So this is a matrix that you encounter in applications. It doesn't look like this matrix has any specific properties, right? It's not symmetric, unless B and C commute, but otherwise it's not symmetric. What it is, though, it's B minus 1 self-adjoint. Okay, so this matrix is symmetric or adjoint for the particular B minus 1 inner product. So again, you just plug into the equations here and you see. So this is useful for looking at properties. In fact, I mean, a very generic statement is that any diagonalizable matrix is self-adjoint for a particular inner product. What do you take for the inner product? Well, you change basis into the eigenvectors, and you take the inner product of the components of the decomposition along the eigenvectors. Yeah.
So you're saying that if you can decompose A like that,
Yes.
then you could simplify the problem in solving.
I'm just saying that A B minus 1 edge is equal to A.
But this decomposition, isn't it always possible? I don't see
No, no, no. For instance, this implies a lot of things. Well, okay. Okay. So it's not always possible. It is. This one, yes. But for instance, okay, so this one has two properties. So for instance, A has real spectrum. And A has B minus 1 orthogonal eigenvectors. Again, to prove this, you just take the proof of the spectral theorem with this inner product. So yes, I mean, so okay. So this always works if you have you can always find a B. So no, this doesn't always hold, but yeah, something similar.
So when you were saying that it's that
Yeah.
like saturation.
No, I look at the map. So I know this in the context of Concham. So in the context of Concham, you take a row n. On this, you build the Hartree exchange correlation of row n. And from this, you build a row n plus 1. And then you iterate. Okay, so it turns out that if you linearize this map, okay, so the linearization of this map is the kernel, the Hartree exchange correlation kernel, the linearization of this step. The linearization of this step is the chi0, is the independent particle susceptibility. And so it turns out that this guy is symmetric definite positive, and this guy is symmetric. And therefore, this map has these properties. Real spectrum, for instance. That's one thing you can prove using this. Yes, with respect to the what you call the kernel.
Just in the context of TD-DFT and other contexts, I think this fact was the name of pseudo-hermiticity.
Okay, I didn't know.
You can
Okay.
change in the product.
Mm.
And,
Okay.
that it is explained in a complicated way, and you say,
I
fact, it is
just
simple.
change it. Yeah. You change the inner product. Change the adjoint. Okay, I have 5 minutes until the break. I will do the SVD. I promised Misson it will be very, very quick. So let's see if I can do this in 5 minutes. Any questions on the eigenvalues, changing your product bit, and so on? So sorry, there's absolutely no structure to the talk I'm giving. I'm just the talk should have been named "Fun Facts in Linear Algebra." Okay, it's more accurate this. No, because I mean, you already know the fundamental bits of linear algebra. So I'm not going to spend 9 hours talking to you about the bits you know. So I'm trying to talk about the bits you don't know, and therefore it's a bit random. Okay, so the SVD. So the SVD is saying that any matrix from Rn to Rm, A is equal to U S V transpose. This guy is orthogonal, or orthogonal, orthogonal matrix. This guy is an orthogonal matrix. This guy is a diagonal matrix. You know what an orthogonal matrix is? Means that U star U is equal to 1. They are orthogonal. Yeah, in this particular sense. Okay, so probably most of you know this, but let's do the proof because maybe most of you don't know the proof. Yeah, so yeah, I will talk about the explanation of this. Proof. A transpose A is STD, no? Well, so okay, so it's not, yeah, it's not, no, okay, it's not. Symmetric. It's symmetric with eigenvalues. Therefore, I'm going to take a complete set of complete and orthogonal sets. This. And we'll have VI orthogonal to Vj. Yes. And now, if I write AX for any X, I can decompose my X into the V's. This is the sum. This is the sum over I of AVI VIX. Okay, and this guy I will call UI almost. We call it UI times sigma I. So meaning I will define UI is equal to AVI over sigma I if sigma I is non-zero. And otherwise I will just drop it. And then I have AX is the sum of sigma I, UI, VIX, which is exactly the ESV. So I told you, yeah, 3 lines, 4 lines. Okay, you just set this and then you find this. So if you put this in matrix form, you get this.
Then how do you show that the UIs are orthogonal?
Right. Yeah, this is a good point. UI, UJ. This is 1 over sigma I, sigma J. Yeah, of course I should have done this. AVI, AVJ. But of course, this is VI, H transpose AVJ. And therefore, this is delta IJ. No, this is not delta IJ. This is sigma I squared delta IJ. And therefore, this is delta IJ. Okay. So let's end this with the geometrical interpretation of the SVD. So let's set n is equal to m is equal to 2, just to see what's going on. What is an orthogonal transformation in dimension 2? Rotation and or reflection. Okay, it's a composition of a rotation and a reflection. So if I take the sphere, you have to imagine this is a sphere, okay, more or less. if I take the sphere in dimension 2 and I pass it through this machinery. So what do I do? First, I apply V. So I rotate or reflect my circle. Then I apply S. What is S? S, so it's a diagonal of sigma 1 until sigma n. So S, these guys are positive. So this will be a stretching of the axis. And then I rotate. Okay. So I have this. Then I pass it through VT. I still get this. Then I stretch. So I will get an ellipse. And you have to imagine this is an ellipse. Then I pass it through U, and I still get a rotated ellipse. Okay. And what are these axes? This guy, sigma 1, and this guy, sigma 2. Okay. So another fun thing about the SVD is that you can write a sort of variational principle. So for instance, sigma 2 here in this particular case is the max, right? It's the eigenvalues. The sigma I squared are the eigenvalues of A transpose A. So if I write this with the variational principle, I have that this is the max of X A transpose AX over X of norm 1. But this is also equal to the norm of AX squared. Okay, and this guy is achieved at V2. So what is V2 and sigma 2? This is the biggest increase in norm by A. Right? If you look among all the vectors in the sphere, which one gets simplified the most by one application of A? It's V2. And how much does it get simplified? By this, okay, sorry. This is sigma 2. This is sigma 1. Yeah. And of course, sigma 1 is the least simplification. So what is the geometrical content of the SVD? The SVD says that you transform a circle into an ellipse, and how much you stretch those axes is reflected by the singular values. Yeah. That's all I wanted to say about the SVD. Yeah, I think so. Okay, so we stop now, we take a break, and then we continue in what, 15 minutes? Je garde le machin, mais tu peux arrêter.
On peut le mettre sur mute pour éviter.
Ouais.
Pas sur mute.
Okay, so let's do it again. So sorry, I was in a bit of a rush for the SVD, so I should do it again slower. So first, the SVD is short for singular value decomposition. So this guy, the sigma i's, they are the singular value. Okay, their square are, so the singular values are positive, real, or non-negative, positive or nul. Bref. Their square are the eigenvalues of A transpose A. So this does look a bit like the eigenvalue decomposition, but it's different. So first, the eigenvalue decomposition has the same guy here and here. Okay, and this one doesn't. So this is very important because, for instance, the SVD doesn't allow you to compute A to the n. Okay, if you try to do A to the n with the SVD, then it's you don't know how to do it, right? Because you got this V transpose U that doesn't simplify, unlike the eigenvalue decomposition. So the singular value decomposition has to do with what happens if you apply the matrix once. Okay, the eigenvalue decomposition has to do with what happens if you apply the matrix a lot of times. Okay, so we've seen before, for instance, with this example 0, 9, 0, 8, 100. So here, the eigenvalues of that were 0, 9, and 0, 8. And they don't give you any information about what happens in the first steps of the powers. Okay? But they do give you information about what happens if you apply this matrix 1,000 times. The SVD, on the other hand, doesn't give you any information about what happens if you apply it 100 times, but it does give you information about what happens if you apply it once. In particular, you will see that the magnitude, this guy 100, will be reflected in the singular value, not in the eigenvalues. If you have a symmetric matrix, then things simplify. Because if you have a symmetric matrix, this guy and this guy are the same. And singular value decomposition is about the same thing as the eigenvalue decomposition. The difference being that in the singular value, we impose that these guys are positive, which is not the case in the eigenvalue decomposition. Okay.
So does this mean that the sigma will be the absolute value of the
yeah.
value?
Yeah. And then there will be some trick to the V will be the minus U. Some trick to make it. Okay. So in some sense, the symmetric matrices are very, very, very nice because the single symmetric and the eigen decomposition and the SVD are the same. And the information, the asymptotic information is the same as the first application information. Okay, and this picture holds symmetric. Any questions on this bit? So the other thing I went quick about is that this guy is the same as this guy. Are you okay with this, or do you want me to explain a bit? It's just, I mean, you just do the multiplication. S is a diagonal matrix. This is what it comes out to. Okay. Any questions on this bit before we move on? Okay. So, yes. So second section, practical linear algebra and high performance linear algebra and how you do this on a computer. So how do you do this in the computer? So you don't have two by two matrices anymore. So you have 1,000 by 1,000 matrices, and I will be very, very brief on this. So there are two main data structures: the plane vectors and the plane matrices, and the sparse matrices and the sparse vectors. Okay. So the plane is simply what you think. It's if you have a vector 1, 2, 3, you store this in memory as 1, 2, 3. You store this as double floats, fine, and then you do your things with this. The main tools are BLAS and LAPACK. Which you manipulate either explicitly if you are doing Fortran or implicitly if you do it with an insane programming language. So BLAS is basic linear algebra subroutine. It's the very basic operations. So BLAS has things for doing x plus y, alpha x plus beta y, dxp, right? It has routines like this. So these are called BLAS 1. It has routine for doing AX. It's called BLAS 2. And it has routines for doing things like this. This is called BLAS 3. So there are 3 levels of BLAS. And the main things they differ on is whether they take as input vectors, or matrices, vectors, or matrices, matrices. The important bit is that you should use in code as far as possible this, or this. So if you have an operation that can be expressed with BLAS 3, then you should definitely do it in this way and not write out the loops by hand. Okay, so this has dot products. A transpose B. Yes. Oui. Oui, oui, j'ai mis sur one. Mhm. Ouais, ouais.
Nowadays, the compilers are so good that it's better to write the loops than to do that one.
Really? Yeah, probably. Yeah, okay. Because it can. Yeah. Yeah, probably. I don't do for fun, so. Yeah, yeah. Hmm. But. Yeah, okay. For fun compilers are clever. But okay, at least for the yeah. Okay, but at least for this one, so this is much more efficient than this. Why is this much more efficient? Plenty of reasons, but the most important reason is that memory accesses cost a lot on computers. Okay, so on computers you have two main costs. Reality is much more complicated than this. You have two main costs: the cost of doing arithmetic, okay, multiplying numbers, adding numbers together, and so on, and the cost of accessing memory. Okay, this is N flops, floating point operation, not per second, just plural of flops. So this plural is a very weird name anyway. You have N flops and N memory access. Okay, whereas for this one, you have N cubed flops and N squared memory accesses. So what this means is that here, you don't see the memory cost too much, at least if you have big enough matrices. Because the memory access is going to be amortized because this is just much more expensive, the cost of doing arithmetic. Okay, whereas if you do this by loops or if you do this naively, then you will see the cost of memory accesses a lot more. Okay, so hopefully the talk tomorrow will cover this a bit, but so for instance, if there's something, this is like HPC in 10 minutes, okay? So don't expect much to be insight. It's just, you should expressing the highest level possible so that your BLAS library is able to do a good job. So one thing that is useful, something called the roofline model. And I'm going to mess up the axis. So the roofline model it looks like this. So in the y-axis, you've got the flops with an S, so the floating point operation per second. So that is how efficiently are you able to use your machine. And on the x-axis, you've got the intensity. Intensity is how many operations you do on each byte of memory. Okay, so these are much more memory intensive, are much more arithmetically intensive than these because they have to do N flops per each byte of memory. Okay, and this funny roofline model is simply fundamental limits. This is the max flops per second just of the computer. The computer can add numbers each fraction of 10⁻⁹ seconds, and so you cannot do better on this. And this has to do with memory access. Okay, memory access is that if you transfer memory from one place to another, if your arithmetic intensity is relatively low, you will get a shape like this. So your application will always be below this, right? Because it cannot transfer memory faster than this fundamental limit, and it cannot compute faster than this fundamental limit. So you will be either here or here, somewhere in the middle. Of course, you will be in practice a lot down than this one. Okay? And by going from BLAS1 to BLAS3, you increase the arithmetic intensity of your code, and so you move here, and so you hope to be faster. Flops is okay. How many? See, this is 1/time, right? So you want to be high on this if you can. Yes. Hopefully, this will be covered more tomorrow. So this was just a bit to explain BLAS and LAPACK and so on. But even, I mean, this is an extremely optimistic model. In practice, you never reach those things. So essentially, the only place where you reach those limits would be if you just do a pure memory copy, or, and even that is hard, or if you do a matrix multiplication. Matrix multiplication is really the only thing that can saturate those, essentially. So yeah, this I'm pretty sure will be covered tomorrow, so I'll talk about it. Okay, so BLAS 1, BLAS 2, BLAS 3, use BLAS 3 if you can. LAPACK is like something that sits above BLAS. It uses BLAS subroutine in the, okay, and the other thing is that BLAS, these are highly, so this BLAS is a standard for this type of operations, implemented by many vendors. For instance, Intel has its own implementation of BLAS. There's OpenBLAS. There's something for Apple. There's something for your machine. And so you should use the library tuned to your specific system. And LAPACK sits on top of BLAS and does things like Gaussian elimination, but in a very clever way, in a block way that allows you to use these BLAS 3 techniques. So this is also because why you should use black box routines as much as possible, because they will use BLAS 3 and you won't if you code things by hand. Okay. So in particular, I mean, BLAS LAPACK. So LAPACK has routines for eigenvalue, for singular values, for everything you want that has value in it. Okay. So that was like dense linear algebra. Of course, not everything is about multiplying dense matrices. So for instance, sometimes you have matrices that are sparse. Sparse matrices are matrices that are mostly zeros, but sometimes you have non-zero entries. It will be fun. Something like this. And so you store only the non-zero elements of your matrix. And then you have specific operations to multiply matrices and so on. Okay. This is asymptotically much faster than this. If your matrix is very sparse, you can do things like A times B much more efficiently than what you would do with this. But it's also much more likely to sit here rather than here, meaning that in practice, the prefactor for doing this kind of sparse problems can be quite big. So if you have things like less than 100 or maybe even thousands of variables, you should probably not use sparse data structures and you should use dense data structures. Just because it's so efficient, yes. I mean, because you have indirect accesses, for instance, for this. Yeah, the memory. Also, you screw the caches. I mean, much more. So for instance, there's some, Jack Dongar, the speaker for tomorrow, he designed a series of benchmarks. The most, I don't know if it's the most, it's his team anyway. So there's something we call the top 500, which is a ranking of computers, supercomputers, according to how fast they can do this. Okay, meaning that it's really measuring this. But of course, nobody cares about doing except for people doing machine learning. So maybe some people care about it. Because machine learning is multiplying matrices. So maybe. But for doing computing, for most often we are probably. And the factor can be quite big. I mean, so there's an alternate benchmark which called the HPCG, which measures how fast computers can solve Poisson equation with a conjugate gradient algorithm. And if you look at the top speed of that, it's like 1% of this. So you probably will never reach this in practice unless you do matrix multiplication. Okay. So this was HPC in 5 minutes. Any questions on this? So the takeaways for this is that performance is complicated. Use black boxes whenever you can, and use black box with higher level stuff, and hope that you fall into this compared to this. The good news is a lot of chemistry actually is pretty prop intensive, so maybe there's a better chance of being here. Maybe you'll here know this much better than I do. Okay. All right. So third part, dimensionality reduction. So assume you have a big problem, like a Schrödinger equation for many, many particles with super large basis sets for thousands of atoms. So you have a big problem set into a very, very big space. Your problem is Ax is equal to B because you like simple problems. Of course, your problem is probably much more like Ax is equal to lambda x. But in fact, the theory of Ax is equal to lambda x is very similar to the theory of Ax is equal to B, but it's simpler for Ax is equal to B, so I'm going to do it for Ax equal to B. So assume your dream in life is to solve Ax equal to B in large dimension. Maybe the large dimension is so large that maybe it's a continuous equation, and you want to solve Laplacian u is equal to f. Let's rewrite it like this. Okay, you want to solve an equation like this. Of course, this is too big to be solved, so I'm assuming that this equation is in dimension n very large. So instead of working on this, I'm going to reduce to a smaller dimension, and I'm going to take k a subspace of n. I mean, I'm saying this guy is big, but he can even be infinite. Then the question is, I want to find x in k such that what? Okay, I want to find x not in the full space, but in a subspace. Okay, so you are in your no, let me do 2D because I cannot draw 3D. So you are in 2D, you want to solve a problem in 2D, 2 is big, and you want to solve now in one dimension. You have a subspace, and you want to solve it there. So what do you do? What do you do in chemistry, usually? You minimize. So what do you minimize? Such that x is equal to min of what? Okay, so we can do that. So what is that? This is not actually what you do in chemistry usually. But let's do that. How do you solve this problem? Well, you write down the optimality condition. So what are the optimality conditions? So this is a criterion that depends on x. And the optimality conditions are simply that for all y in k, I have to have that ax minus b is smaller than ax minus y minus b. Okay. Plus 1. So we can expand this, and we can compute the gradients. And so you do this, it's standard exercise in calculus. You compute the gradient of this. And what this is saying is that ay ax minus b is equal to 0 for all y in k. Yes? You want me to do this or you okay? It's just computing the gradient of this guy. Yeah. So you will get that is AX A K. When I write this, it means that K is a subspace. So AK is the set of all AX for X in K. Yes, the action of an operator on a subspace.
X is the argmin of the.
Yes. Good to have mathematicians in the audience. Belongs. Okay. So this is called, I don't know how this is called. Sometimes it's a Galerkin, sometimes it's a Petrov-Galerkin, sometimes it's a whatever Galerkin, sometimes it's a Ritz, I don't know, these names. It's never clear which this is. But this is not actually the standard Galerkin method. Why? So for instance, you can write this in a basis if you want to see what it does. And write this down in the basis. So you have a basis E1 to En, or maybe I call it, how do I call it? I think I call it V in my notes. I think I call it V, yes. So if you have an orthogonal, no, not orthogonal. If you have a basis V is equal to V1 V small n. Okay, these notations are the same as the ones in the book by Sads because they are nice. So if you have a basis of K, what do you have to do in order to solve this system? Well, I mean, you just write it down, right? So you write X is equal to sum of Xi Vi, and you write that what has to happen is that AX minus B times, yeah. So A Vi times AX minus B has to be equal to 0 for all I. Then you expand this into this, and you find out that X should satisfy the equation A transpose AX. No, sorry. So V transpose AV times small x is equal to V transpose V. Probably. No, V transpose, yeah. V transpose A transpose V. Yes? So V, I write it as a matrix like this. So A is so this has big N here and small n here. Okay, it's a matrix, which is what people call tall and skinny, so many more rows than columns. So AV means applying A, which is an operator, a general operator. Think of the Laplacian or something. Applying A to all the columns of V, and then you build these inner products. This is not what you do in chemistry. What do you do in chemistry? When you solve the Hartree-Fock equations in your favorite Gaussian basis sets, you don't compute these matrices, right? Because these are too big. This is A transpose A, so A transpose A is complicated to build. So if you think of quantum chemistry, you would have A is equal to minus Laplace plus a potential, and this would have terms like V squared or Laplacian of V, which is not so nice. So this is not usually what you do in quantum chemistry. What you usually do in quantum chemistry is instead of this condition, you do or AX minus B orthogonal to K. and then you drop an A. You drop an A transpose. So this is the more usual Galerkin thing. This is what you do, right? No, because I mean, this is the matrix element you compute. What you compute in practice is that you compute things like VI, A, VI. So this is your Hamiltonian, and then you compute VI times Vj, which is your mass matrix, which doesn't come up here because we want to solve Ax equal to B, but would come up if you wanted to solve Ax equal to lambda x.
The first method, is that related to the least square method?
Probably, I mean, this is a least square. So,
Yeah. So it's related to the least square. And the second method is something like
so it's least squares, but not least squares as the usual. Well, is it? Yeah, no, it is least square. It is a least square. Yes. And the second one is probably more the Galerkin methods, the standard Galerkin methods.
This comes from the theorem that you have.
What do you do? Not another way. No, the second one is a choice that you make. So, but where does this come from? Okay. So this was one thing. So let's call this the least squares method. So good things about the least squares method, it's simple to formulate. It's reasonable to minimize the residual. Okay. Ax minus b is called the residual. So I want to minimize the residual here. It's reasonable, but it's bothersome because then you have to compute things with the square. It's not to say that it isn't useful. It is useful in many contexts, in fact. Even in quantum chemistry. It's more, anyway. So this is one thing. The other thing you could do is instead of minimizing this, you take x in k such that x is equal to argmin. And instead of minimizing a residual norm, I'm going to minimize an energy. So if A is symmetric, then it is the same. It's not the same, but it will compute the same thing because the solution of this guy, if you minimize this over the whole space, you minimize this over the whole space, you find your solution. You know this. Okay, and if you have an eigenvalue problem, and you instead of doing this, you do this, but with the constraint that x has to be from 1. So this is the Galerkin method. What does this correspond to? If you write down the optimality condition is that y times ax minus b is 0 for all y in k. Okay. In other words, ax minus b is orthogonal to k. This is Galerkin. And then if you write down this down in the basis, you find this, which is much nicer because you don't have the a squared. Okay, so these are two instances of a more general method, which is the projection method, which is x in k such that ax minus b is orthogonal to L. So if L is equal to k, this is least squares. If L is equal to ak, no, sorry. If L is equal to k, this is Galerkin. If L is equal to ak, this is least squares.
Guy here is a variance.
It's a variance minimization. I mean, so you'd have to write this for eigenvalue. Here I've written down for Ax equal to b, which is a bit weird. If you write this down for the thing is that I don't think this works for eigenvalue problems, does it? No, it's because it's non-linear in lambda. No, it's non-linear in lambda. If you
So you don't have to do
yeah,
uh,
but it's a non-linear minimization.
yes.
No. Yeah, you can
That's why it's-
Yeah, this is probably a better explanation than the a squareds. Yeah, if you do this for eigenvalue, it's not nice.
that could be, Bayesian function or
Okay.
mathematical.
Okay. I don't know. Yeah. Yes. No. No. You see, here you have to compute the matrix element of A transpose A. Whereas here, you just have to compute the matrix element of A.
The eigenvalues of A transpose A are the square of the eigenvalues of A transpose A.
Yes.
Then it's like you want diagonalizing the square. So
It's something like that. Here I've explained it for Ax equal to B, not for X equal to B, but yeah, it's related to that. Yeah, it's the same as if you were to do A transpose A.
So like the stationary well, only that like the arc, like the minimum point is the same with the manifolds. So like if you look at the space.
Yeah, it's well, it's not. So the minimizer is the same. Well, I mean, so the minimizer, the global minimizer of this is the first is the solution. No, yeah, but no, here, yes, it's the same. Yes, for Ax equal to B, yes, it's the same, but the Hessian is different. The Hessian of this is A. The Hessian of this is H squared.
This one is more
Yeah, this was for, I mean, not for Ax equal to B, but for X equal to lambda X, it's more nonlinear. But it's also more. It's also a bit more robust in the sense that it will not fall prey to the same kind of issues that you will have for instance, for continuous spectrum. This might be more interesting than this. Yes. Yeah.
So the general method will be the case, for example, of Kappa cluster calculation, where
Yes.
you select your
Yes.
projective space as
Yes.
single and double excitation, and then
Yes.
you don't beat, and if you don't do that, you don't do the scalar scheme, but you.
Yes. You can pick another basis set. Yeah. Yes. So this is why for linear problems, I mean, I will talk about this probably tomorrow, but for linear problems, these give rise to different iterative methods. Yeah. Yes.
Those two are equivalent only when A and C.
They are not never equivalent. They are never equivalent. Ah, yeah. So if if A is ED, yes. Otherwise, no, but I mean, no, for a specific set of K, they will never give the same. This is restricted to K, so they will never give the same answer. It's some kind of oblique projection, right? It's you coming back to this. So this is K, the subspace K. You want to approximate some point, some true point, which is here. And so you can minimize different things. And depending on this, you can get different results. So maybe you get a projection like this, or maybe you get a projection at an angle or something. But you will not get the same results with this and this. But hopefully, I mean, the hope is that when K becomes complete, when you approach the large basis set limits, then both methods will work. You usually have better theoretical guarantees really depend on the structure of the problems. Yes. Yeah, of course.
Can we say anything about the other spectrum reports?
Of what?
Like you're looking for harmony, but for
Yeah, I mean, the stationary points of this are the eigenvalues. So this is a bit tricky because you can get stationary points, but really you're not interested in any stationary points. You're interested in, yeah, I mean, yeah, you see the stationary point would be, I'm confused because because these are the first order conditions. So this is unique and this is also unique, right? So there's only one in both cases. There's only one. Yes, because you see it's given by this equation. You're thinking of eigenvalues. So in the case of eigenvalues, there are many stationary points. And here, but here you will get, here you would also get many eigenvalues.
This one is a subset of that one in the case of it.
It's not even a subset. It's, I think it's completely different. This guy is fully non-linear. This guy is linear. And no, there's no particular reason why it would be a subset. But this one has, so for instance, this one approximates from above, and this one doesn't. Yeah. Yeah, when you want to do eigenvalues, because when you want to do eigenvalues, you want to do, I want to minimize x minus lambda x over all x of norm 1. And but the lambda is given by the Rayleigh quotient. So if you want to do this, the only way to do it is in this way, and then it's non-linear, and therefore it's non-quadratic, and therefore the equations are non-linear. Whereas for the Galerkin, you just do this, you minimize x transpose Ix with respect to x, and then you get a linear thing.
And you said that for continuous spectrum, this method is more powerful.
So I mean, there are people claiming things like this.
Is there a particular reason which you can understand that?
I hesitate to say stupid things. You get a control on the residual, and therefore, if you are able to go from the residual to the error, you're in better shape. And you also get some kind of idea of error bounds with this method, which you don't get with this. Because with this, you can compute this. Whereas with this, you have no error bounds at all. You just get eigenvalues and that's it. So you can get some quantification of accuracy with this, which is better. Anyway. So Galerkin methods. To one general structure, which is really this guy. It's very simple. I want to select the x in K such that the residual is orthogonal to some subspace. Two main avatars, L is equal to K, which is the usual Galerkin method. L is equal to AK, which is the least squares. Okay. And you've got an analogous picture for the eigenvalue problem as well. Okay, so more generally, you can do something a bit different. You can take any subspace you want if you have a better idea for what those squares would be. In particular, maybe if you want to do non-symmetric eigenvalue problems, maybe it's better to select this to be a better approximation of the left eigenvectors than this one of the right eigenvectors. So you can play with this kind of things. Anyway. Yeah.
So you prefer the method on the right or on the left? For accuracy?
It's hard to say. This one for eigenvalue for x equal to b. For x equal to b, both usually work. So because I mean, the main reason I'm talking about this is because then I will introduce conjugate gradient Krylov methods and so on, and it turns out that this is CG, this is GMRS. Both work about the same. I'm not sure I will have a preference. I don't know. Yes. Yeah, so okay, so V is a bit tricky because I'm using the same symbols here for X and the components of X. So this I really shouldn't have done. So how will I call it? I will call this C. This is the component of X. And so here is a C. So C is the component of X. X is the abstract vector. C is the representation in the basis set. This is why you have a V that connects both. Yeah, this was a very bad choice. But with this, I think it's better. Yes, it's good. Okay. So for instance, with this, I mean, the approximation of a minus one, so the real solution is a minus one. With this, the approximation is, so if W is, going back to the general setting, right, with this one, if V is a basis of K and W is a basis of L, then you write down that X is approximately, let me just not mess up, V times W transpose AV minus 1 times V transpose B. Right, this is just writing out this equation, or this equation, and generalizing to a case of any basis of L. Okay, so you can see it as a sort of approximation of A minus 1, because this is A minus 1B. You can see it as an approximation of this. So one particular instance, for instance, if you take A is equal to identity, then you get that any vector B is approximately V times V W transpose V minus 1 V trans. Oh, this is a W, sorry. No, this is a what? Yeah, it's a W. Yes. So this is an approximation of the identity. You can see it as a resolution of the identity. So here you have your vectors of your basis, and here is a kind of dual basis. Right? This guy here is a dual basis. This is the basis against which test your things. Okay, so for instance, you can see that if W is equal to V, this is just, so this is this guy. Sorry, this is, yeah, both are the same in fact in this case. This is just orthogonal projection. You project orthogonally onto your subspace K, which is the same as L in this case. Otherwise, it's some kind of oblique, non-orthogonal projection. Yes, two specific case. So, yes. Yes. Because this was again for the Galeckin. This whole thing is Galeckin. This whole thing is these squares, and this is a general projection method. This is a generalization. I will give some examples of this. So yes, so this guy, you can call this thing here. You can call it Z transpose, and Z will be the dual basis. Convenient thing also. No, you know K, you fix K. So K is typically your subset of Gaussian basis functions. Hopefully, yeah, then of course you should play with this. But so another thing, another nice thing you can do about this dimensionality reduction and things that are similar to this is you can do compression of an operator with this kind of same kind of base of things. So what this is saying is that this this you say that so with the identity you say that identity is approximately V times Z transpose. And Z transpose is the basis set, which is given by this, which is a kind of orthogonalization, but with a different set of vectors. It's a dual basis construction. So if you have any operator A, you can approximate A by plugging this resolution of the identity. So you can say that A is approximately V Z transpose A, V Z transpose. Okay, and then you have to compute these matrix elements, but there are not that many of these, and you get an approximation of your A operator. And this has a lot of applications. So for instance, the one you might be familiar with is resolution of the identity for computing four-center integrals, for computing the Coulomb integrals. So for computing the Coulomb integrals, you have a mapping from the ij to the KL, okay, which is given by these Coulomb integrals. Okay, this is just a big tensor ijkl, and you compress those with an index, I don't know, alpha, it's an index beta. And so you've got the same okay, either you know what I'm talking about or you don't care. But if you know what I'm talking about, it's you have the codensities and you write the codensities from the basis. And you can write them in this form. And then you have exactly the same kind of you can formulate it in this way, which is a very elegant way of formulating. And then you have different flavors of resolution of the identity, because you can minimize different things. You can minimize the overlaps. You can minimize the energy and so on. And that's, you can plug in this form and get different things like this. So it's a very general framework that whenever you have an operator, you can compress it in this way. And this, you just have to compute a reduced set of elements. This is called the low rank representation of A. And of course, Misson is going to talk about this much more. So applications to quantum chemistry would be resolution of the identity. There's one application, maybe the people here are not that familiar, but pseudo potentials for plane wave codes. So this is more for the condensed matter crowds, but you do pseudo potentials whenever you're on a plane wave basis. So what you find is you find the pseudo potential angular momentum by angular momentum that will give you better states that will not oscillate quite so much. It's called effective core potential in chemistry. So essentially, you would approximate V by a sum of PL, VL, PL, where this guy is a projector on angular momentum L. And this V, you have different potentials for each angular momentum channel, and this allows you to get better states. And it turns out that this operator is very complicated to compute in practice, because you have to compute X-ray symbolic of this guy. And what you can do is you can do a reduction where you can say, I don't actually need this guy to be exact on all states. Okay, I don't need to compute. This is an approximation you always make, right? But then this guy, this operator, I don't need this to be good on all spaces. I don't need to have this particular form on all states. I needed to have a good form on each of the orbitals of the atom. Okay, and then you can use again the same kind of compression because you can say, I take these orbitals, these are a subset of my space, and then I compress my big operator, which is complicated to compute, only on these orbitals. So this is called the Kleinman-Bylander form, which is a low rank compression of this certain potential of this. Yeah, I don't know if you care about that or not. Okay. Yeah, another example is something called adaptively compressed exchange, which is a way of making the exchange compression go faster. But again, maybe this is for plane wave basis, and you folks don't care about it too much. But anyway, it's also an application of these kind of ideas. It's a direct application of this kind of. Okay. So this concludes the reduction of dimensionality part. Any questions on this bit? No? Okay. So now linear problems. As if we have not done already too much linear problems. But I want to talk about linear problems in the sense of how do we solve AX is equal to B on a computer. So again, with the AX is equal to B, I like AX is equal to B because it's where you can do things in the most general way and in the simplest way. AX is equal to lambda x is very similar to AX is equal to B. In fact, AX is equal to lambda x, you can see it as a nonlinear problem, and as a nonlinear problem, if you are close to a solution, it's like a linear problem. Okay, you can linearize it. So therefore, AX is equal to B is relevant for studying AX is equal to lambda x. And also, it's relevant because much of the theory is the same. You've got also the same kind of Langshaw's process and so on that I will talk about. Okay. So linear systems. AX is equal to B again and again. So I want to solve this. Let's say now that I fix this is in our n big but manageable. How do you solve this? Well, so first, can you solve it? It depends on whether A is invertible or not. So let's assume that A is invertible. Again, if A is not invertible, we have the Fredholm alternative that we talked about before that tells you exact condition for this to have a solution. But assume it's invertible. If it's not invertible, you can do things like pseudo-inverse or regularization, but maybe I don't get into this too much. Okay, so some quantitative properties of this. First, what is the sensitivity of this equation to perturbations in the coefficients? So let's say that instead of solving this problem, I solve because I've got an error. Maybe it's the error just because I have to store my right-hand side and my matrix on my computer, and so I don't exactly compute this that I thought I was going to compute. I actually compute something like this. Delta B is a variation in B. Okay? For simplicity, I'm keeping A the same, but you can do the same analysis with a different A. Okay? So I'm going to write it as A plus, as A x plus delta x equal to B plus delta B. This is relevant for a number of things. I mean, the most basic is that you make a mistake just because of computer arithmetic ones. Can I compute delta x? Yes, very easily, right? Because AX is equal to B, so I just subtract and I find that delta x is equal to A minus 1B, delta B. So of course, the more A is close to being non-invertible, the bigger this guy will be. This is no surprise. Then I'm going to introduce something called the condition number A, which you may have encountered already. This is Why? Because I want to say that the norm of delta x is norm of a minus 1 times delta b. And here I'm going to be a bit more specific on the norm. So instead of doing like I did before, I will take this as the operator norm, which is the max of ax over x for x non 0. Which is the biggest singular value. It's not the biggest eigenvalue, it's the biggest singular value. For a symmetric matrix, this is the eigenvalue. The biggest eigenvalue. Okay? Sometimes people do triple norms for matrices. I'm just going to do double norms. All right, this is good. So why am I not happy with this? I'm not happy with this because this depends on, for instance, units of A. If I change the units of my system doesn't change. It should not be harder to solve my system if I measure this in R3 or in E. Okay, but this bound tells me it does. So this is because I haven't computed the relative error, but I computed the absolute error. So what I would like to do is a bound like this. Yeah, usually when I talk to mathematicians, I have to explain a lot why. When I teach to mathematicians, I have to explain a lot why this guy matters, but I'm talking to chemists, so I don't have to. Okay. So here I need something delta B over B. So what do I need to put here so that this works? Well, so I just need to put B over X. And by what can I bound this? Did I screw up? Oh, yeah. So because, what? Yeah, it's good, okay. So because B is AX, and therefore I can say that this is smaller than norm of A, norm of X. And this goes away. Oh, sorry, and I still have to carry that I minus 1 here. Okay, and in the end, I can write that norm of the delta X over X, so the relative error. No, I messed up again. No, this is good. This is good. Okay, so the relative error in X is bounded by some coefficient times the relative error in B. What is this coefficient? This coefficient is the ratio of singular values of A. So let's do a simple case. If A is symmetric, what is this guy? A is the condition number. This is the definition of the condition number. Kappa of A. Condition number. So if A is symmetric, then kappa is lambda n over lambda 1. It's the max. It's the max of the lambda over the min of the lambda. So it's good because this is a unitless number. It's a dimensionless number. It's completely intrinsic to your problem. Well, completely intrinsic. Well, no, it depends on the norm again that you put. So it depends on the inner product. So if you change the inner product, you change the condition. That's life. But if you have a symmetric matrix, then you know what inner product you should take is the standard Euclidean product. And your conditioning is the biggest eigenvalue over the smallest. Okay. So in some sense, it's a measure of how different the scales of your problem are. So if you're doing a quantum mechanics computation, maybe this refers to what is the biggest energy of your system over what is the lowest eigenvalue energy of your system. Maybe this is linked with a gap or something like this. Yes.
So I think the condition number was a small number.
No, it's a big number.
So
It's
how-
always bigger than 1. Yes.
So if you want to compare that with the arithmetic of your computer, which is a
Yes.
small number.
It's 10 to the you have to take 1 over kappa. So if you yes. So I mean, so for instance, this tells you this guy is 10 minus 16, right?
Yes.
In practice. So this guy is 10 minus 16. So if you look at the errors made by the computer, what this tells you is that the relative error delta x over x is the condition number times 10 to the minus 16. So if your condition number is 10 to the 5, it's relatively okay. If it's 10 to the 16, then you have no chance of getting even 1 digit right.
So if you want to be on the safe side, so you should go. Are you allowed to go to 10 to the minus 40, or you stop well before?
I don't know if I would call this safe.
So should I stop at 10 to the minus 7? Or
10 to the minus 7, probably you can. It depends on the accuracy you want. The machine accuracy, right? But I mean, usually you're limited by other factors, right? So this accuracy, you don't care about getting this to 10 minus 16 because you're doing you solve a model problem anyway. So a good rule of thumb is that kappa times the error that you make here will be much smaller than the precision, the chemical precision you have.
so can I give you a quick example?
Yeah.
So I want to do a DIA for
Yes.
going to get like matrices that are more or more same.
Yes.
So my condition number
Yeah,
can
blows up. Yes.
increase very fast.
Yes.
I still want something meaningful.
Yeah.
So when should I?
So
What is the best value?
So definitely, I can tell you what I've done in my code. I've set this to 10 minus 10 or something. So it depends on a lot of things. So first, this will be the accuracy on the DAS coefficients. The coefficients are going to multiply something that is small anyway, so it's not that big a deal if it blows up a bit. Also, I mean, the coefficients, you don't care about getting them to 10 to the minus 10 precision, right? So if you get them to 10 minus 4 or something, it should be relatively okay. So a good rule of thumb is that the kappa should be definitely smaller than 10 to the 16, much smaller. How much smaller depends on how much how courageous you feel. Yes. You have to, sorry? Sorry, yes. Yes. No, so this is when you want to solve AX is equal to B. I know that you guys don't care so much about AX equal to B, but I care about it because it's simpler. So if you want to solve AX is equal to lambda X, then the question is a bit different. The condition number, but I will talk later, probably on Wednesday. I will talk about the conditioning of the eigenvalue problem. And on the conditioning of the eigenvalue problem, you will see that the gap will appear and you will see things like this. But this is different. I want to talk about this in a simpler context first. Yes. The eigenvalues for lambda in the spectrum. Sigma, not to be confused with the singular values. Sigma is the spectrum, the set of eigenvalues. By? No. This has nothing to do with how you solve the system. This is completely intrinsic. Even if you have the best methods you can think of, it will still solve this. So yeah, as soon as you have a small error in your data, this is the error in your data, right? It's not not the error in your iterative procedure or something like this. So it's completely intrinsic. You cannot bypass this.
Decrease delta B by iterating.
Yeah, but there's a fundamental limit to the delta B, which is machine precision, for instance. And this you cannot go below. What you can do is you can compute your residual in extended precision, and this decreases the thing, and then you can do things. But otherwise. Okay. So this gives some error estimates and introduces the condition number that we are going to see later on in more details. How do you solve this in practice? What is the simplest method that you know how to solve this? If I give you a school children problem, Paul has twice the age of Jack, Jack has 2 more candies than John, and so on, and put the linear system into equations. How do you solve this? Gaussian elimination. Right? What is Gaussian elimination? You have A, B, C, D, E, F, some coefficients like this. You subtract, so you have L1, L2, and so on. You subtract a multiple of L1 from the other rows in order to get zeros here. Yeah. You do it once, then you do it for the seconds, and so on. You know this. So Gaussian elimination. What is the complexity of Gaussian elimination? As a function of n? It's n cubed. Why is it n cubed? Because you need, okay, so you do this once, then you introduce the zeros here, you introduce the zeros here, so below the diagonal, so you manage to get a matrix which is like this, but has zeros here. You do this by reduction, and then you go back, because then you can solve for the last unknown, right? And then you propagate back. So complexity is n cubed. Why is it n cubed? Because at each step, so you have n step of your algorithm, and at each step you have to modify all these entries. So you do basically O of n cubed, n squared work. It's a bit complicated. It's a bit different this because it's a triangle, not a rectangle. So there's a factor coming in, but for big O's, you don't care. Okay. So this is n cubed work, which of course is huge. I mean, if you have a big matrix, this is huge. So what can you do better than Gaussian elimination? So first, if you have a sparse matrix, then you are in luck. Well, you are not in luck with Gaussian elimination. Because in fact, if you have a sparse matrix, if you try to do Gaussian elimination, it kind of blows up because you get fill-in, because you destroy the sparsity structure when you do Gaussian elimination. So there are techniques around this, but they are not super always reliable. So complexity. So fun fact, it's nobody knows what this is. In fact, nobody knows what the optimal constant here, what the optimal power is, exponent is, because the complexity of Gaussian elimination is the same as complexity of multiplying matrices, in the sense that if you can multiply matrices fast, you can turn that into an efficient algorithm for doing Gaussian elimination recursively with short complements and so on. And so nobody knows what the asymptotic complexity of matrix multiplication is. It's somewhere below 2.5, or I don't know what people do these days, but nobody knows. Okay. So to implement this thing, of course, you should never do it by yourself. You should call your black box LAPACK favorite routine. And LAPACK is going to expose this in the LU form. So this is a matrix factorization of the same kind of we've seen before. You write A as the product of L and U. So L will be triangular lower and U will be triangular upper. So essentially, this Gaussian elimination, I will not do this because this is insane to do. It's super annoying to do, to prove this and to write this in details. But basically, you manage to go from your matrix here to an upper triangular matrix by doing operations that are triangular inferior in nature. This will require some explaining, but essentially this is how you get this. Anyway, so assuming you get a factorization like this, it's easy to solve ax is equal to b, right? Because if I want to solve lux is equal to b, I can solve lux is equal to b. How do I do that? Well, I mean, this is triangular, right? So it's easy to solve a triangular system. So I solve this system, and then I know ux, and once I know ux, I can solve for x. Yes? So the reason why this is exposed by the cause, one of the reasons is by this form, you can compute a lot of things that you would not be able if you just code Gaussian elimination in a standard way. So for instance, you can compute determinants. If determinants are very bad, never use determinants. So in fact, in 3 days, I don't think I'm going to talk about determinants once, except to say now don't use them. You can compute things like if you have ax equal to b, but then later you want to solve ax equal to c or different c, then you can just do the work of factoring a once. And once you've done this work, this costs n cubed. But once you know this, solving this is n squared. Okay, so you do the work of factoring a once, but then for each right-hand side, you can reuse the factorization.
So the LU factorization, you see that as a variant of Gaussian.
Yeah, it's an algebraization of Gaussian elimination. It's just writing out what you do when you do Gaussian elimination by hand. If you want to do this more systematically on a computer, pretty soon you find this form. Yes. So there are some tricks. You have to take care of pivoting because you cannot divide by 0, or you cannot divide by something that is too small, and so you have to be careful about that, and so on and so forth. Yeah. It's not going to this. So this is the first factorization. No. The second one would be L transpose. This is Cholesky. So if you have A, which is LUP, it's essentially a variation of LU. I'm going to. This is just like, this is twice as fast as LU, but that's about it. And it respects the symmetry. So it's nicer if you have a symmetric matrix, but that's about it. Well, you do two in one step, because essentially when you do these operations, you know, you do L1 minus L2, and so you will do things like this. So sorry, L2 becomes L2 minus alpha L1. And these coefficients, from these coefficients, you compute the L. Yeah, there's some, yeah. Because here you compute square roots, where here you don't. There are some differences, but functionally they are the same in the sense that we do the same job for like half the cost, but that's about it. Okay, this is Cholesky. Cholesky is useful for a number of things like computing orthogonalization. Another thing that you might come across is A is equal to QR. So Q is orthogonal. So in here, L is the same as here. It's triangular lower. And R is triangular upper. This is another name for Gram-Schmidt. So you know in Gram-Schmidt, you find the Gram-Schmidt would be Q is equal to A R minus 1. So in Gram-Schmidt, you obtain an orthogonal matrix by doing triangular manipulations on the columns of A, essentially. So if you just invert, you find A is equal to QR. I mean, I could do 1 week on this if I wanted to kill myself. I could do 1 week on this because there are many things to say about how you write this in details and so on. It's super annoying, but it can be done to do this in practice on a computer. So there are many ways of computing this. There's Gram-Schmidt, there's Jacobi, there's Householder, there's plenty of names like this, but they are functionally equivalent. So this is useful for getting orthogonal basis as well. And yeah. So all of these can be used to solve Ax equal to b in different settings. So for instance, if you do this on MATLAB or Julia or something, you do this like this, A\B. So the backslash operator, A\B will solve this, and it will solve this by trying to do various factorization routine depending on what A is. If A is square and symmetric, it will try to do the LR transpose. If A is rectangular, it will try to do a QR and so on and so forth. Okay. So of course, these methods are only working for small, relatively small matrices, dense matrices. If you have bigger matrices, then you have to use something else. So this is the topic of iterative methods. How much time do I have left? Should I stop now? Okay, so probably I think I would stop now because all the rest will take more time. So yes, let's stop now. Any questions on this bit or the other bits? No? Okay, so tomorrow we do various methods around Schur complement and so on, and then iterative methods, Scherzen methods, conjugate gradient, GMRS, and so on. All right, see you tomorrow.
Don't leave anything valuable in the room. Don't drop.